Hello everybody, welcome back. Today we're going to be looking at Unit 9.7, which is on the topic of galvanic and electrolytic cells. However, I just wanted to tell people that are watching this, I'm going to hold off on covering electrolytic cells until Unit 9.10. It just makes more sense to me to put it there. So I'm going to be talking about galvanic cells today. So let's get started. So both the concepts of galvanic cells and electrolytic cells fall under the overarching umbrella of electrochemistry, which is exactly what it sounds like. It's the interchange between chemical and electrical energy. It's using chemical reactions to harness electrical power. And in order to discuss electrochemistry, we need to review some terms. We need to review the concept of a redox reaction. All right, so let's review a little bit of vocabulary. And I gave you all before, when we first talked about redox, this little mnemonic device. Leo the lion says grr. And these letters stand for something, that when an element experiences a loss of electrons, meaning its oxidation state, its charge would increase, that is the process of oxidation. If an element experiences a gain of electrons, that would mean the oxidation number, the charge decreases. That is reduction. Okay, and remember that in a redox reaction, you have to have one of each. You always have to have something being oxidized and something being reduced. Okay, so this is review. And in redox, if you will recall, we were looking at an overall redox reaction, you could look at that overall reaction sort of split into two, what we call half reactions. Okay, and you can see that the copper ion, the copper 2+ ion, from left to right is being converted into solid atomic copper. Its charge has gone from +2 down to 0. So what must have happened? It must have gained 2 electrons. Copper is the element that has been reduced, whereas elemental solid zinc has been converted to a zinc 2+ ion. What must have happened? It must have lost 2 electrons. So zinc is the element that has been oxidized. Okay, and what happens here, okay, this is called a galvanic cell, and I'm going to go into much more detail on this, but essentially we can use these two half reactions and cause electrons to flow through a wire. An electron, moving or flowing electrons, that is electricity. So we're using chemical reactions and turning it into electrical energy. So let's just look at this. All right, this is the very, very simplified setup for a galvanic cell. Okay, these are the same two half reactions we were just looking at on the previous slide. Okay, zinc is the element on the left and it's being oxidized. Copper is the element that is being reduced on the right-hand side. And I want you to notice that in these half reactions, the zinc half reaction is producing, releasing, getting rid of, however you want to say it, 2 electrons. And where are those 2 electrons going? Are they just floating off into space? No, they're not. Okay, so what we've got here essentially is 2 beakers, and in the beaker on the right, I'm going to sort of do a little bit of labeling, and we're going to look at this in more detail in just a second. This yellow bar would be a solid bar of zinc, and this sort of greenish liquid would be an aqueous solution having zinc ions floating in it. Maybe it's a solution of, zinc chloride or something. Doesn't matter, as long as it's a solution that has zinc plus 2 ions. And then over on the right-hand side, this bar would be a solid bar of copper, and this pink solution would be some kind of aqueous solution that has copper plus 2 ions floating in it. And this white line here, okay, that is a wire that is connecting the zinc bar to the copper bar. So again, as I said, look at the half reaction on the left. Zinc is giving up 2 electrons. And where are those electrons going? Well, guess what? They are going to travel through the wire in that direction because the zinc reaction is giving up electrons. And that's awfully convenient because look at what is happening to the copper reaction. It is needing to take in 2 electrons. And that's really convenient because that's the reaction on the right is looking to give up 2 electrons. How nice. So we can pair these 2 reactions in a setup like this and cause electrons to flow through a wire, and ladies and gentlemen, that is electricity. Okay, and guess what? And again, we're going to talk more in detail about this in just a minute. A galvanic cell, you know what is a much more simple word to describe a galvanic cell? A galvanic cell is a battery, ladies and gentlemen. And what do batteries do? They provide power. Okay, so this is a very, very simplified description here of what a battery looks like. Okay, so this is how you can link 2 redox half reactions and cause electrical energy to be generated. But there's a problem with the way that I've drawn this here. It says with this setup, the system will start, meaning electrons will flow through the wire, but then it's going to stop immediately. And the question is why? Like I would only be able to generate any power for maybe a second. Why would it stop? And those of you that are in physics, I want you to think about circuits. This is not a complete circuit. Okay, if you think about what we just described, the electrons in this picture are going to flow from left to right, and that's wonderful, but that's going to create an imbalance of charge. We're going to get, if electrons, let me just draw that one more time. If electrons are constantly flowing in that direction, we're going to get a big buildup of negative charge in this, what we call a half cell. And we're going to get a big buildup of positive charge in the left half cell. And that's a problem, okay? To have a circuit flowing, you've got to have sort of a conveyor belt of charge. And so, how do we fix that? Well, let's look at a much more detailed setup of a galvanic cell. And again, it's using the same half reactions we've been talking about. So, there's a lot going on in this picture. Let's break it down. Okay, so first of all, the same half reactions we've been looking at. Okay, zinc on the left is being oxidized. Oxidation is taking place in the left half cell. Reduction with copper is taking place in the right half cell. Okay, and you can see the solid zinc and solid copper, and they are connected with a wire, and it's showing right here how electrons are flowing. Okay, in the middle of the wire is a device called a voltmeter. Okay, that's not impeding the flow of electrons. It is literally just measuring the voltage that is flowing through the wire. It's just a measure essentially of how much electricity is flowing through the wire. The higher that number is, the more electricity we get. Okay. Now, as I said, one of the things to notice, okay, is that if we did not have a completed circuit, electricity would not flow for very long. So how do we fix that problem? We put in what is called a salt bridge. And remember what we said on the previous slide. If electrons are flowing in this particular diagram from the left half cell to the right half cell, that would result in us getting a big buildup of negative charge here and a big buildup of positive charge in that beaker. So how do we fix that? We put in what's called a salt bridge, okay, which is some sort of porous medium. It could literally, guys, it could literally be a strip of a paper towel if you wanted. Something that allows ions to flow through it. And not just any ions, but spectator ions. Ions that are not a part of this redox reaction at all. Ions that are not going to interfere with the reaction. And if I'm getting a big buildup of negative charge over here, how do I counterbalance that? Well, how about if we have something positive with a spectator ion, like a sodium ion, traveling this way through the salt bridge? That would balance out that buildup of negative charge. And how do I fix this problem of getting a big buildup of positive charge on the left side? Well, how about if we have a nice spectator ion like nitrate flowing this way? That would counterbalance this big buildup of positive charge. And as I said, guys, sometimes a galvanic cell can have a salt bridge as simple as a strip of paper towel or something absorbent, like a sponge maybe, soaked in a solution of sodium nitrate. As long as it is extending into both half cells, that could serve as a salt bridge. And the purpose of a salt bridge is just to complete that circuit to counterbalance any buildup of charge. Okay, let's look at some other things here. Okay, let's look at the left half cell, this half reaction with zinc. Okay, zinc, if you look at what's happening to it, solid zinc is being converted into zinc ions. And look at this blown up picture here of that zinc electrode, the bar there, that's called an electrode. And look what's happening to it. The solid atoms of zinc are being converted into aqueous ions that will then be floating around in the beaker. So if you think about it, guys, this electrode, this zinc bar, is actually losing mass over time. It's slowly disintegrating. So if we measured the mass of that zinc electrode, and then we started up the galvanic cell and let it run for an hour or two, and then measured a final mass of the zinc electrode, we would find that the mass has decreased. Okay, and mass, you can't eliminate mass. It has to go somewhere. Those solid zinc atoms have been converted into aqueous zinc ions that are now floating around in the beaker. And then look on the other side. What's happening to this copper half cell? Copper ions, look at the picture, are coming out of solution and are attaching themselves to that copper electrode. Zinc ions are being converted into solid zinc. So this electrode is gaining mass over time. If we measured the mass of the copper electrode before and after, we would find that the copper electrode is actually heavier than it was at the start. Okay, one final thing I would like to point out. This half reaction is oxidation. this half reaction is reduction, okay? Wherever oxidation is taking place in a galvanic cell, that half cell is called the anode. Wherever reduction is taking place, whatever half cell, wherever that is taking place, that half cell is called the cathode. And ladies and gentlemen, electrons always flow from anode to cathode. Always, every single time, no exceptions. Electrons always flow from anode to cathode. And you know how that's easy to remember? That's alphabetical. From A to C, electrons flow from anode to cathode, always. Okay? And you know what? It's alphabetical this way too. Electrons will always flow from the side where oxidation is taking place to the side where reduction is taking place. So, let's talk about one other thing, and then we're going to look at an example. Okay, so as we've now noticed, galvanic cells have to have some kind of solid electrode immersed in some sort of solution. But here's the question. What if the species involved in the galvanic cell reactions, what if those are not solid? Like, what if they're liquids or aqueous or a gas phase? For example, like, what if one of my half reactions was this? Okay. This guy and this guy are both aqueous species. There's no solid, okay? There's no solid iron involved in that half reaction. They're both aqueous. Well, we have to still have a solid electrode. That is a need in a galvanic cell. So if one or both of your half reactions do not have a solid in them, usually we will use a platinum or a graphite electrode because they're conductive. They'll conduct electricity, but they are, for the most part, very unreactive. They're not going to interfere in the reaction. So in that case, with iron +3 going to iron +2, those two ions would be floating around in the aqueous solution in the beaker, but the electrode itself that's immersed in that solution would be made of platinum or graphite, something like that. So this is just an example question. And we've got a galvanic cell diagrammed on the right-hand side, and we've put in the direction that electrons are flowing. In the next unit, we're going to look at how would you know that without being told. Like, I'm telling you in this diagram which way the electrons are flowing. In the next lesson, you're going to learn how to figure out, without being told, which way would they be flowing. So let's answer some of these questions. The first question says, which half cell contains the anode, right or the left? B says, what will happen to the mass of the zinc electrode as the cell operates? And then the final part says, describe the motion of the ions in the salt bridge, meaning are they flowing to the left or to the right? Okay, so let's look at this one at a time. So the first question says, which half cell contains the anode, right or left? Justify your response. And let's remember what we said. I think I said it 3 times. Electrons flow from anode to cathode. Okay, so this aluminum half cell, the one on the left, is the anode. Electrons are flowing from that half cell, indicating that oxidation is taking place there. So the left half cell is my anode. Okay, the second question, part B, asked, what will happen to the mass of the zinc electrode as the cell operates. Okay, well, I know that the zinc side, that's my cathode, and wherever the cathode is, that's where reduction is taking place. And this half reaction for this zinc half cell is taking place between zinc and zinc plus 2. So if it's being reduced, I want you to think about what that half reaction would look like. Okay, and if you're thinking correctly, it should come into your mind that it's going to look like this. Okay, because zinc is being reduced from plus 2 to 0. Okay, so I said the mass of the electrode will increase, okay, because aqueous zinc ions are reduced to solid zinc atoms, and those atoms are deposited on that cathode, on that zinc electrode. You could say either one. Okay. All right, last part. Part C says, describe the motion of the ions in the salt bridge during the cell's operation. So remember, the whole point of the salt bridge is to balance out that flow of charge. And based on this diagram, the way electrons are flowing, we're going to get a big buildup of negative charge over here and a big buildup of positive charge over here. Okay, so look at the spectator ions that are in the salt bridge, and let's think about which way they have to be flowing. So those potassium ions, because they're positive, they must be migrating to the right half cell to balance out that big amount of negative charge, whereas the nitrate ions are going to migrate to the left to balance out the buildup of positive charge. So this is a problem that is very similar to the one that we were just looking at. This one, you'll notice, does not have arrows indicating which way the electrons are flowing, but if you read the question carefully, there is a way that you can figure it out. So I want you to pause your video and see if you can figure this out. All right, so part A said, identify the electrode at which oxidation is occurring. Explain your reasoning based on the student's observations. And if you'll recall, the student noticed that the tin electrode, the one on the right, was it losing mass? Let me go back up. The tin electrode was correct, yes, was losing mass, was decreasing in mass. So, since that is the case, since the student observes that the tin electrode is decreasing, that must mean that those tin atoms are being converted into tin plus 2 ions, and that is oxidation. So the right-hand half cell, the tin electrode, is where oxidation is taking place. Part B says, as the mass of the tin electrode decreases, where does this mass go? You can't just destroy mass. That's conservation of mass, of course. So these tin atoms, as we said above, are going into the solution as tin ions. Okay, you can't destroy mass. It has to go somewhere. Part C says, in the expanded view of the center portion of the salt bridge shown in the diagram, draw and label a particle view of what occurs in the salt bridge as the cell begins to operate. And we did not have to draw solvent molecules, and we were to use arrows to show the movement of particles. So I drew something just simple like this. Okay, so if electrons in this drawing, and you know, electrons are not always in a galvanic cell diagram going to flow left to right. In this case, electrons are flowing from the right half cell to the left half cell. That means there is a big buildup of negative charge in the copper side, which is why the potassium ions are going to flow to the left into the left half cell. Since electrons are leaving the tin half cell, there's going to be a big buildup of positive charge on the right-hand side, which is why it would be helpful to have nitrate ions flowing to the right. So, I hope that you have now learned a little bit of something about how galvanic cells work. Remember, a galvanic cell is nothing more than a battery. So I hope that you have learned a little something today, and I look forward to seeing you next time.